Hi my dear students, today we will start section 3 in chapter 18, Chemical Equilibrium. Last 2 weeks we finished natural of chemical equilibrium and shifting equilibrium. This week we will start equilibria of acids, bases and salts. But before starting you have to review and understand KW, and you know what's the meaning of KW, which is equilibrium constant of water, self-ionization of water, K equilibrium and its equation, constant equilibrium equal concentration of products power 2 coefficients over concentration of the reactants power 2 coefficients. And finally, common ion effect should be also understood. Now, let us see the first slide. The pH of the same concentration of different acids are different. Why? This is according to the ionization degree of each one. The more ionized one, which is HCl, due to the less pH, which means more acidic strains. So HCl is more stronger than CH3COOH, which is acetic acid. So in this slide, let's see the concentration of HCl is 0.1 molarity, and the concentration of acetic acid is the same, 0.1 molarity. Why is the pH of this concentration of HCl different from the pH of the same concentration of acetic acid? Why? Because of the difference in ionization. As we know, HCl is a strong acid, so it is completely ionized, so it has this H will dissociate and connect with the H2O in the solution to form hydronium ion. So all molecules inside the solution will form hydronium ions. But in CH3COOH, as it's very weak acid, small amount of this H will ionize to form hydronium ion. So the pH of HCl is less than the pH of CH3COOH. So HCl is a strong acid and CH3COOH is weak acid. By the same way, if we have a concentration of NaOH 0.1 molarity and a concentration of ammonia solution 0.1 molarity, so the same concentration, but NaOH as a strong base, so it's completely ionized, but NH3 is weak base, so it is not completely ionized. So the pH of NaOH is more than the pH of NH3. So NaOH is a strong base, but NH3 is a weak base. So now our objectives in this section is to explain the concept of acid ionization constant and write acid ionization equilibrium expressions. Second, review the ionization constant of water. Third, explain what is the meaning of buffer or buffering. And finally, compare cation and anion hydrolysis. As we mentioned before, K equilibrium is the equilibrium constant, and we mentioned it by KEQ. This KEQ equal concentration of the products power of the coefficients over the concentration of the reactants power to the coefficients. By the same way, the Ka is called acid ionization constant. Acid ionization constant. And by the same way, we can calculate Ka as follow. If we have reaction or ionization of, for example, acetic acid, now acetic acids will hydrolyze or ionized in aqueous solution to form hydronium ion and acetate. Now this part is the reactants and this side is the products. So the equation for Ka by the same way like K equilibrium, Ka equal concentration of the hydronium ion power to the coefficient times the concentration of the acetate ion power to the coefficient. Here the coefficient equal 1 because the equation now is balanced equation. 1 mole of acetic acid well ionized with 1 mole of H2O to produce 1 mole of hydronium ion and 1 mole of acetate ion. So Ka equal concentration of hydronium ion power 1 times concentration of acetate power 1 over the concentration of the acid, which is the acetic acid, also power 1. We have inside this reaction a factor, which is the self-ionization of water. And return to section 1 to understand what's the meaning of self-ionization of water. But this self-ionization of water does not affect the value of the Ka. Why? Because it is in state of equilibrium and does not affect the value because it is because the concentration of water is not included in the equilibrium expressions. And as we explained before, the ionization constant is specific at a specific temperature. So for each temperature we have specific ionization constant. But if we change the temperature, we will have another ionization constant. As we see in this table, now ionization data and constant for some dilute acetic acid solution at 25 Celsius are given below. Now the molarity, which is the concentration, now concentration decrease down the table, the percent of ionized molecules increase down the table. Why increase? Because you have dilute solution, so this dilute solution will facilitate more molecules to be ionized. So now here you have also the product, which is a hydronium ion. You have high concentration of the hydronium ion and also high concentration of acetic acid. So in this table you have increased concentration down the table, increased ionization down the table, decreased a number of hydronium ions down the table, also decreased a number of acetic acid down the table. And if you remember the equation, this equation here, you have value of hydronium ion above and you have another value of acetic acid down. So here, if you increase this value and decrease this value and decrease this value, the constant or the Ka still constant and it reflects the value in the table. Here all these values are almost the same. Why? Because you don't have any effect in the main equation. if you decrease the amount or the concentration of hydronium, you have to decrease also the amount of the acetic acid concentration. So the conclusion here, if you increase the concentration of this acid, you have to increase also the product of hydronium ion, and the net result is no effect in the Ka, which is the ionization equilibrium or the ionization constant. This is for normal ionization of a weak acid. But now, if you remember the common ion effect, if you increase the acetate ion by adding of sodium acetate to this side, what will happen? Now you have high concentration of acetate ion, which will react with the hydronium ion to produce acetic acid again, return to the common ion effect. So adding of sodium acetate will disturb the equilibrium and shift the equilibrium to the left side or to the right side, return to the common ion effect. Now you have high concentration of acetate because you add sodium acetate to this side, and you have hydronium ion, so acetate will react with the hydronium ion to produce acetic acid, so the equilibrium shift to left. So the concentration of hydronium ion increased or decreased? Will decrease due to consumption with acetate ion, and the concentration of acetic acid will increase or decrease? Will increase, because of it is a product of the reaction between acetate and hydronium ion. So this disturbance causes a decrease in the concentration of hydronium ion and increase in the concentration of acetic acid. The equilibrium is reestablished with the same value of Ka, because Ka is constant at specific temperature, but there is a higher concentration of non-ionized acetic acid molecules and a lower concentration of hydronium ion in the left and the right side. Changes in the hydronium ion concentration affect the pH. If you have a low concentration of H3O, this will increase the pH or decrease the pH. It will increase the pH to the side of alkalinity. So the solution now, it will change the pH of the solution, and it will be close to 7. So now for our chemical reactions at equilibrium, if you will add common ion to this equation at equilibrium, this common ion will affect the equilibrium and shift the equilibrium to the left side or to the right side. What will happen, or how can we establish the pH if we add a common ion? We can explain this process by explaining what is the meaning of buffer. Buffer, the solution, are solutions that resist the change of the pH. Buffered solution contain both a weak acid and a salt of this weak acid. So if we have a reaction like this reaction, CH3COOH plus H2O to produce H3O positive plus CH3COOH. If we apply the buffer process or the buffer concept to this solution, we will add weak acid, which is acetic acid, and the weak or the salt of this weak acid, which is sodium acetate. So we have to add mixture of acetic acid and sodium acetate to this solution to avoid any change in the pH during the chemical reaction. So for this reaction, if we add buffer solution, which is a mixture of acetic acid and sodium acetate to the solution, it will fix the pH and avoid of any change in the pH during the chemical reaction. Let us explain this picture. Now this comparison between buffered and non-buffered solution. Here the beaker on the left side contains a buffered solution and an indicator with a pH of about 5. The beaker on the right side contains mostly water with a trace amount of acids and an indicator also. The pH meter shows a pH of 5 for both of the two beaker solution. So on the left side you have two solutions. One contains a buffer and the other does not contain a buffer. But before the reaction or adding of anything from outside, the pH indicate 5 by pH meter. Now after adding of 5 milli of 0.1 molarity HCl to the solution, what will happen? For the left one, the color of the solution is still as it is. That means this solution which contain buffer does not affect it with any change in the concentration of the acid. As we know, if we add acid to the solution, it will shift the solution to the acidic line. So it will be to the right, or in the pH scale it will be to the right side, or to the left side it will be to the left side, near to the acidity. But here we add 0.1 molarity HCl is added to both beakers. The beaker on the left side does not change because it has buffer, indicating no substantial change in its pH. However, the beaker on the right undergoes a definite color change. Why definite color change? Because the indicator now will be an acidic media, so the pH is now 2.17, so the color will change from purple color to yellowish color, and the pH meter shows a pH of 2.17. So it is acidic media because you don't have in this solution any buffer solution that will establish the pH. So if a small amount of acid is added to acetic acid sodium acetate solution, the buffer, acetate ions will act with most of the added hydronium ions to form non-ionized acetic acid molecules. Non-ionized acetic acid molecules. The hydronium ion concentration and the pH of the solution remain practically unchanged. By the same way, if a small amount of a base is added, the OH ions of the base react with and remove the hydronium ions to form non-ionized water molecules. So in both cases we have non-ionized acetic acid and in case of acid, and in case of base we have non-ionized water molecules. Acetic acid molecules then ionized and mostly replace the hydronium ion neutralized by the added OH ions. The hydronium ion concentration and the pH of the solution remain practically unchanged. So in both sides, if you have a buffer solution, there is no change in the pH. What is the benefits of buffer solution or buffer action? Buffer action has many important applications in chemistry and physiology, like inside our body. In human blood is natural, which is naturally buffered to maintain a pH of between 7.3 and 7.5. For example, if you will take like any pills like aspirin, the chemical structure of the aspirin is acetyl salicylic acid, so it is acid. So if you take 2 or 3 pills of this aspirin, what will happen naturally if you don't have buffer inside your blood? The acidity of the blood shift to be alkaline or to be more acidic. Sure, the concentration of the acid will increase in the blood and the acidity increase in your blood. What will happen? There is a huge disturbance in your biological system. There is stopping of the enzyme activity, problems to our cell metabolism. So our human blood should be buffered solution to avoid any change in the pH. Thank you, hope to understand. See you.